last speaker for today is Viv Mehta, talking about numerical algebraic geometry, a new perspective on string and gauge theory.
Okay, thank you very much for inviting me here. And I'm basically from lattice QCD background. Okay, so but Young and James Gray have been encouraging me to work on string phenomenology. So since my PhD, I've been working on this numerical algebraic geometry methods, which are very recently developed methods, and I'm trying to apply it to particle theory in general. And this is for the first time I've been working on this specific area of particle physics. So my motivation is as following. We always encounter nonlinear equations, right? It's very natural to have nonlinear equations in any problems you work on. For example, finding all the string vacua or stabilizing moduli spaces and so on. In potential energy landscape scenarios, we have to find all the critical points where we have to solve nonlinear equations. And of course, it is well known that nonlinear equations are very difficult to solve. But if you have polynomial system of equations, polynomial equations, then you are still in business. Okay, that's the whole point of my talk. And even if you might not have polynomial equations in the first place, you might try to convert them to polynomials, and then you can apply all the methods that I'll be describing in this talk. So I'll try to be a mathematician here. So just for the moment, I want to address this problem. I have a system of nonlinear equations, n of them, in m variables. Okay, so and I want to solve all of them simultaneously, and I want to find all the solutions, not just one or few of them, all of them. And number of variables and number of equations may or may not be equal, but I'll stick to m is equal to n case for the moment. So as I said, even if you may not have polynomial equations in the first place, say you have some equation of this kind, then also you can convert it to polynomial by taking say sine and cosine as S and C, and then so your resulting equation would look like this, and then you add constraint equations, sine squared theta plus cos squared theta minus 1. Okay, so this combined system of equations is a polynomial equation. Similarly, if you have tangent in your equation, then tangent is a naturally algebraic variable. It takes values from -∞ to infinity, so it can be taken as an algebraic variable only. Similarly, if you have this complex conjugate, the variable and its complex conjugate, then it is not a polynomial equation, but you can take x is equal to a plus ib, put it here, and then x1, and then you get rid of this complex conjugation. Okay, so you again have this polynomial equation, and so on. There are many tricks available in literature and in some of my earlier papers. If you have some transcendental equations like exponentials, then it's kind of tricky. Okay, but still in some cases, Gray et al. Have given a brief trick. They said that if you have very few transcendental functions, then you might be able to convert those transcendental functions to algebraic variables. Okay, so anyway, so I always take a very silly example to explain my method. I'm taking this example. I want to solve this polynomial equation. It is very silly. You can solve it by hand, obviously, but let's pretend that we can't solve it by hand. So I would use two of the methods that are available on market. Firstly, it's a Grosvenor basis method, which is a symbolic method, and most of us have been using this for ages now. And it is symbolic method. Even if you use Mathematica solve command, you would be using this unknowingly. The other method is called numerical algebraic geometry method, which is developed very recently in 2005 and 2006, and I somehow introduced this to lattice field theories, and it turned out that I was the first one who introduced this in the whole particle theory, although I should have been the last one to be working on algebraic geometry methods. But anyway, so just a lightning review on the Grosvenor-Bayes method. You all know about this, so I'll be very brief. When you have a system of equations, polynomial equations, there is a well-defined algorithm called the Buchberger algorithm. Okay, what it does is it takes the system of equations you want to solve and converts it to an easier system. Okay, and the point is that the new system and the original system has the same solution space, so you obviously solve the easier one. Okay, you don't need to know the algorithm to do that. There are well-written packages available online for free. Singular, Cocoa, Macaulay 2, even Maple and Mathematica have inbuilt commands, and there is this string vacua package available from the Oxford Durham group, which is a Mathematica interface of this particular package. So you don't need to know the commands of Singular, you just call it from within Mathematica. Okay, how is it useful? So in our running example, I asked Mathematica to give a Grosvenor basis for that system, so it gave me this. Okay, so how is it easier to solve? If you look at it closely, the first equation is univariate, and the rest of them have increasingly more variables. So you solve the first one very easily, then back substitute it here and here, and you solve the whole system exactly. There is no numerics involved, right? It's a symbolic method, and in this case there are 3 solutions, 1 real and 2 complex. I mentioned this in a very general manner, but there is a better way to use Grosvenor-Bayes method, and that involves elimination and decomposition method. You could see it in Gray et al.'s paper of 2006. So that was a short review on the Grosvenor-Bayes technique, just to make the talk self-consistent. I want to concentrate on this new approach. It's called numerical algebraic geometry method. Here, say you have a system of polynomial equations to be solved. What you do is you have 3 steps procedure. Firstly, you estimate an upper bound on the number of solutions. Okay, so the crude most upper bound on any system of polynomial equations is the so-called Bayes-Wood bound, which goes like this. If you have a system of polynomial equations, the maximum number of solutions it can have is the product of degree of each polynomial of the equation of the system. Okay, so in our case it was they all were quadratic equations. So 2 to the power 3, 8. 8 is the maximum number of solutions it can have. Okay, not necessarily it will have 8 solutions, but maximum. I have written this running example in the vectorial notation just to make a later expression easier. So then the second step is to construct a new system which has 2 properties. One, it should have the same number of solutions as the estimated upper bound, and the second one is that the new system should be easier to solve. So for this running example, I constructed this equation, this system, right? It is very easy to solve, and it has 8 solutions. Then the third step is track each solution of this new system using this homotopy. Okay, I should explain it a bit further. So here I have constructed this homotopy where if you take t, the parameter t, to be 1, then this term vanishes and only this term survives, and so you know all the solutions of this system, right? So you pick up one of the solutions here, then you track t is equal to 1 from t is equal to 1 to t is equal to 0. At t is equal to 0, if you reach there, then this term vanishes and only this term survives, which is your original system to be solved.
Sorry, by solutions, what do you mean? Like prime ideals or?
This is zero-dimensional ideal right now.
Okay, so you.
So only isolated solutions.
Okay.
So you do that for each of the solutions, each of the 8 solutions, one by one. You track each of the paths, and then in the end, some of the paths will converge to F, and some of them will diverge. In this case, we know that there are 3 solutions, so only 3 paths out of 8 will converge, and all the others will just diverge. Okay, so that is this method. Here you would wonder what this factor is. This factor makes sure that all the paths behave are well behaved. So there is no singularity in between the paths. This is very important. Okay, and this guarantees to find all the solutions in the end. So there are again well-written packages available online. Bertini, Home for PS2, PHCPack. Just a brief comparison between the two methods. In the Grosvenor-Bayes technique, you can get exact solutions. Here you can get numerical solutions, obviously. But there is a sharp difference between the Newton-Raphson method or any other method. Here you can get all the solutions. Okay, this is sharply different than any other method. The second difference is that the algorithm here is known to have exponential space complexity, which means that the RAM required by the machine would exponentially blow up if you add one more equation or one more variable and so on. Okay. Here there is no such scaling problem. This algorithm is highly sequential, which means that each step in the algorithm requires the knowledge of all the previous steps. Okay, so you have to use only one processor. Here it is called embarrassingly parallelizable. Each path can be tracked independently of each other. Okay, so if you have a big cluster, you can embarrassingly parallelize this method. Non-integer coefficient is a problem here. It is here this is just a numerical method, so any coefficient is fine. I took this example to demonstrate the efficiency of this numerical approach. I took this paper, and these were the K and W, and in the end V looked like this. So I wanted to find all the stationary points of this V. Okay, and there are 9 equations and 9 variables here. String vacua, the package, could not solve it completely. Okay, it gave some information, but it could not solve it as we know we mean by a solution, which means that singular, the interface could not solve it. Whereas a numerical algebraic geometry package, one of the packages solved it in 10 minutes on a regular desktop. Okay, this was a classical Bezier bound. These many paths I had to track, and in the end I got all the solutions. Okay, so that was all about the case when only isolated solutions exist, so the zero-dimensional ideal. But I also worked on positive dimensional ideals, and I showed that I could get the complete irreducible decomposition of those ideals. And this paper was published, recently accepted, and it was with Young, and Jonathan Howenstein is one of the authors of Bertini package. Okay, he helped us a lot in solving some of the systems using his cluster. We are also now working on numerical elimination and numerical Hilbert series computation, and that paper should be out very soon. I'm also working on numerical algebraic, numerical enumerative geometry, and potential energy landscape in statistical mechanics scenarios. I've been working on that a lot. I think I put 7 papers or so in the last 2 years in this theoretical chemistry and statistical mechanics point of view. And I'm also talking to Liam and Fredrik to work on the string theory scenario in the potential energy landscape. And I'm also talking to Alexander Westphal and Markus Rummel to find critical points of some potentials. So in short, symbolic methods we all know and we have been using extensively, okay, the whole string phenomenology community. But I personally think that these methods are running out of the steam. We have more and more complicated problems and we can't solve them using the existing methods. So it is time to learn this numerical algebraic geometry method. It is completely parallelizable, so you can solve very difficult problems as well. And it is in true sense a 21st century method. So I propose to use this, and on that note I'll stop here.
Questions?
Yeah, I think the example problem you gave us, how many actual solutions were there?
Only 12.
12?
Yeah.
So it's kind of the same question as before, but can you deal properly with prime ideals of dimension bigger than 0? Because sometimes you decompose in prime ideals, but in the end what you get is as horrible as the original problem, and you cannot deal with them.
Here I can give you only the full irreducible decomposition, which means that I can give you all the positive, all the dimension, all the components and degrees of
But then
each
you have to solve them.
No, I mean once you know the degree and dimension of the component, what do you need?
You need to solve them to find the structure of critical points that maybe depends on 1 or 2 parameters, or 3 or whatever the dimension
Okay,
is.
so the parametric systems is I haven't worked on it. But if you just want to have irreducible decomposition, then it is very easy. I mean, we have already shown it.
How sensitive is this method to the condition in the numerical analysis sense of the equation? I mean, usually when you solve these problems, you sometimes have big hierarchies between the parameters. So it could be that something is set to 0 by accident numerically, while it is different from 0 in the actual solution. So have you checked? I mean, can you always apply this, or does it pretty soon run into problems due to?
No, I think you can always apply it. I mean, you can use adaptive precision. So at each step of this path tracking, it will decide what precision it should take. Okay, so I mean, we have this state-of-the-art algorithms. So those problems are not there. Those numerical accuracy problems are not there. I don't know if you have some very specific.
I mean, but just wondering. Usually they are badly conditioned, or it can have.
Yeah, I mean those problems can be dealt with these days. It's not big problems these days.
No question? Okay, let's thank the speaker again.